Let's take a look at surface area of revolution. Now we've already seen arc length, and last year we saw volume of revolution. But what we're going to think about now is if we do rotate something about the x-axis. So if we rotate about a function about the x-axis, obviously a volume, like a three-dimensional shape, would be formed. But we can also find the surface area of that shape as it's rotated around. Okay, it doesn't find like the full surface area if you think about it. It just finds the area of this rotational surface as it moves around the shape. Okay, if it was like a 3D object and you wanted to find the full surface area, this could be like a modelling style question, you'd also have to find the area of the base and the top. And they would, if you think about that, they'd just be circles, wouldn't they? And you could figure out what the radius of those were. The radius of those circles would just be the y values. So, but for now, we're just going to focus on the actual outer surface around this as it's rotated around. Again, we look in the formula booklet. There's two types. It could be Cartesian, it could be parametric. We're going to start with the Cartesian one, y equals cosh, rotated about the x-axis. First thing I want to do is think about what 1 plus dy by dx looks like. So if y equals cosh, dy by dx would equal shine. So 1 plus dy by dx squared would equal 1 plus shine squared. We know cosh squared minus shine squared equals 1. So this would equal cosh squared. Let's set up our integral. Okay, so the surface area about the x-axis is 2 pi. Integral of y, which is cosh x, times by the square root of 1 plus dy by dx squared, which is cosh squared. We're going from 0 to 2, x values, because this is a Cartesian integral with respect to x. And let's see what we've got. So we've got 2 pi. Square root of cosh is cosh, so this is cosh squared. So if we're familiar with the original one for the normal trig functions, the hyperbolic one is very similar, cosh 2 theta, 2 cosh squared theta minus 1. So cosh 2x plus 1 all divided by 2 is the identity that we can use, because we're trying to integrate cosh squared. I'm going to take the half outside, so that would be 2 pi over 2 cosh 2x plus 1. Cosh would become a half shine 2x plus x, limits 0 and 2. With this being a show question, let's just be careful, make sure we get to the right answer. So that'll be a half shine of 4 plus 2 minus. If we sub 0 in, shine of 0 is 0 and 0. The answer that we were aiming for was 2 pi outside. Okay, so think about this as if we wanted to multiply by 2, we'd be taking the 2 outside of this bracket. I don't know why they've actually done that. So you can think about this as 2 lots of a quarter. Shine of 4 plus 1. So then that 2 could come outside and it'd be 2 pi. 1 plus a quarter. Shown at 4. Okay, next one's taken from a past paper question. We're given parametric. Okay, let's just read the question carefully, because obviously we've got to make sure we're doing the right formula here. It says the arc from t equals 0 to t equals 2 pi is rotated through 2 pi radians. So it could be a volume we're about to find, but it says to generate a surface. Okay, so we've got parametric, we're thinking about the surface area, and we're aiming to show that the answer looks like this for the first part of the question. So this one is the parametric version for the surface area. Don't just substitute everything in straight away. Let's just start by thinking about, well, what's the x by dt? Okay. So minus cos becomes positive sine, so that becomes 2 sine. 2t dy by dt would equal 4 cos t. So we've got the x by dt squared plus dy by dt squared. Again, possibly pause and see if you can get to this answer before I go through it. If we do the x by dt squared, that's going to give us 4 sine squared 2t plus 16 cos squared t. Always have one eye on the answer that you're trying to get to here. I need to do something with this 2t, don't I? So we can think about that as 4 lots of sine 2t, which is 2 sine t cos t, all squared. And that gives us 2 squared, which is 4, so 16 sine squared cos squared t plus 16 cos squared t. Now this allows us now to take a factor out. We can take 16 cos squared and be left with sine squared plus 1. So I think that's going to be useful when we sub into the formula, because when we square root, if we can square root this, that allows us to just use the fact that the square root of AB we know is root A root B. So by factorising this, I can tidy this bit up quite nicely. So let's set up our integral, so it'll be 2 pi. We're going from 0 to 2 to pi over 2. Y, which was 4 sine t, square root of this stuff, which would be 16 cos squared sine squared plus 1. So we're nearly there. Split this out up. That would become 4 cos t. I could do something with this, because I'm noticing that we can use an identity potentially here. Well, actually, can we 1 plus sine squared? I mean, we'll have to think about that one in a second. That might be a little bit awkward, actually. But I'm looking at the answer, I need to leave that there, don't I? Okay, so this is going to give us, in the form that we required, take the 16 out, so 32 pi sine t cos t square root of 1. plus sine squared t dt between 0 and pi over 2. Part B actually says we want to evaluate this. Okay, so hence find s in the form pi over 3 m root 2 plus n, and it tells us m and n are integers. This is probably the most challenging substitution question I've seen when the substitution has not been given. So this is taken from a 2018 paper. Like, I've just had a look at it and I was thinking, well, what substitution could I use? Like, initially I thought we were going to do an identity here, but it doesn't work because it's 1 minus sine squared would be cos squared, so we can't use an identity to help us to tidy the square root up. It comes down to spotting that this function inside the other function, that's where the problem lies. Like, that's non-linear, isn't it? Like, what we've essentially got is 1 plus sine squared t. It's the power of a half. And that's where most of the substitutions lie, when there's a function inside another function. And if we just look at that, if we do let u equal 1 plus sine squared, so all of that thing, if we write as u, just a quick check to do the derivative, so du by dt, the 1 disappears, times by the power, times by the derivative, take 1 off the power, and then I noticed that, there we go, look, there's a non-linear function, and the derivative is outside, so when we rearrange, they're going to cancel. Not an easy one to spot, but don't forget you're always looking for that function inside the other function, and also the derivative gets paired with the outside. Okay, so if we let u equal this, du by dt would equal this, so we could replace dt. So we get sine t, cos t, and then square root, this is what we're calling u, and then dt we can replace with du, divided by 2 sine t cos t. Simplifying this down now, they cancel, take the half outside, and we're left with a very simple integral, u to the half, which is the beauty of these substitutions. Like, it turns something completely horrific just by spotting where the problem is, and then we get a nice, relatively straightforward question from here on in. Okay, we've got 16 pi, add 1 to the power, dividing by this, so let's multiply by 2/3. And we've got limits, which are t values. Okay, so when t equals 0, u would equal, go back to this, sine of 0 is just 0, isn't it? So u would equal 1. And when t equals pi over 2, u would equal sine of pi over 2, which is 1. So 1 squared plus 1, u would equal 2. So just tidying this up, we got 32 pi over 3, subbing our limits, 2 to the power 3 over 2 minus 1 to the power 3 over 2. The form that we need, let me just check. Okay, it is. So we got pi over 3, m root 2 plus n. Okay, so I need to put this 32 back inside, and I just need to tidy this bit up here. Okay, 2 to the 3 over 2 is 2 to the 1 times by 2 to the half. And that's where this root 2 is going to come from. So we'd get pi over 3, 64 root 2 minus 32. Okay, thanks guys.